Hey pre-cal, welcome back. So we are going to be continuing to add to your trig identities that you have done. So hopefully you have that paper out or your notes out and you can add this as well. We're going to be talking about some multiple angle identities. So in the last video that you did, or we learned about the sum and difference identities. And so this is really going to build on that. So this homework part 2 is more practice that we encourage you to do as well after you have reviewed this video. So let's get started. So just like I showed towards the end of the last video, there's these school yourself videos that we encourage you to take a look at, especially to see like where exactly these are coming from and to get a more in-depth understanding. So if you haven't already done so, you might want to find some time to take a look at them. And so since our focus today is double angle, or in this lesson is double angle and half angle identities, right? So you did sum and difference. Those are really the two videos that I would suggest you go ahead and take a look at. This is linked on the PowerPoint, as is it linked on the actual page for this week in IB Pre-Cal. So here's our double angle identities. And it ideally doesn't take much for you to take a look at this and really see how it links with what we did in the other video, right? So we did the sum, and if you remember for cosine, if you have cosine of A plus B, that's cosine of A, cosine of B, minus sine of A, sine of B. And this is assuming, like, we don't know what A and B are, right? But if we're dealing with a double angle here, I could write 2 mu as the cosine of mu plus mu, right? And they're the same angle. And so when I go ahead and I fill this actually in, I would get the cosine of mu times the cosine of mu. Oh, wait, those are the same. Minus the sine of mu, sine of mu, right? And so that's why it's cosine squared minus sine squared. And so this right here is the double angle identity for cosine, right? These are just different ways that we can express it. Do we see how? Well, let's go back to our favorite identity, the one that comes up in everything, the Pythagorean identity, right? And that was sine squared plus cosine squared of an angle equals to 1, right? And so if we know that, we've got this, right? So I could actually go ahead and just replace the cosine with 1 minus sine squared, right? So if I've got 1 minus sine squared, so just replacing this, minus sine squared, oh, isn't that just this? 1 minus sine squared minus sine squared. So all I did here was I just took cosine squared mu and I replaced it with its equivalent from the Pythagorean identity. I'm going to do the same thing here. And instead, though, I'm going to replace sine. So I'm going to take cosine squared mu minus, and then sine is equivalent to 1 minus cosine. 1 minus cosine. And you're going to see this happen a lot today. And if I go ahead and I distribute that minus, I end up with cosine squared mu minus negative, that's plus. So that's why it's 2 cosine squared mu minus 1. So these are just manipulations, right? And hopefully, as we've recognized at this point, you don't need, or we don't ideally want to have all of them memorized. There's certain ones that, yeah, you might, that will come up more, but you can come up with them or derive them or figure them out from the context that you're given without necessarily having to memorize them and having a true understanding of it. If we take a look over here at sine 2 mu, well, if we remember again the sum for sine, if we had sine of A plus B, we had sine of A cosine of B plus sine of B cosine of A. I might have just flipped that up, but that's okay. You can multiply in either order. And so, well, if A and B are the same, right, if they're both just mu, then I'm dealing with sine of mu, cosine of mu, sine of mu, cosine of mu. And that's why it's just, you're like adding it to, that's why it's just 2, right? So that's where this is coming from. This is an important one. And from these two, we can come up with tangent, right? Just like you can, you know, the quotient, right? So I could go ahead and do something like 2 sine of mu cosine of mu over cosine squared mu minus sine squared mu. And I could, I did something like this in the last video. I could factor out cosine squared. If I factor out cosine squared in the numerator, I'm going to end up with 2. That cosine is going to go away, but I'm still missing one. So it would be sine over cosine in the numerator. And then the denominator, I would just end up, if I factor out cosine squared mu, I would end up with 1 minus sine squared over cosine squared, which cancels. So I end up with 2 tangent over 1 minus tangent squared mu. Oh my goodness, check that out. Pretty cool, right? You can come up with that. So we also have the half angle identities. And so what this is getting at is if you're trying to find, and similar when we were talking about the sum and difference, if you're trying to figure out the sine or cosine or tangent of a specific angle that is not a special angle, but it's double, like you can use double one, you can use the half angle, right? So like, some of these things, like you might be able to use half angle, or maybe you could use subtract, like the difference, or you might be able to use like, right? So there's going to be like different pathways to the correct answer, but you want to be familiar with using them in the event that you're asked to use them, right? Especially as we're learning it right now. So you might be wondering about the plus or minus, and that would just depend on the angle, right? Like if I was dealing with the angle pi over 8. Well, that's a good one, right? Pi over 8, not a special angle, but, well, that could be pi over 4 over 2, right? And now I have an angle. My mu is a special angle, and so I could figure this out. So I could figure out the sine of pi over 8, right, using this half angle identity. I lost my train of thought, though. Oh, the plus or minus was what I was going with, right? And so pi over 8, you would just want to think to yourself, okay, so if I'm on the unit circle, pi over 8 is going to be in quadrant 1. Well, the sign in quadrant 1 is going to be positive. So your answer is not going to be plus or minus. It's going to just be dependent on what we're working with here. And so just as we did in the last video, I would encourage you to go ahead and actually add these onto your paper or your notes where you have your identities. And so you have them all in one place as you're reviewing and practicing and prepping. So you've got sine, you've got cosine, and you've got tangent, and we're gonna look at applying some of these. The proof for this is a little more involved. It's actually in this PowerPoint. I'm not gonna go through it, but if you have downloaded the PowerPoint, you, I believe, will be able to see it. And take a look at this video for more information about it. Okay, right, important. So before we move on, why couldn't the identity sine 2x equal 2 sine x get alone? Think about what we just talked about. It needed a cosigner, right? Get it? It needs a cosine. It needed a cosigner. Amazing. Okay, let's return to this, to the math. So we also have one that we're going to look at, which is the power reducing identities, right? So if you have something that is raised to a power, like how do you quickly, and you might have different pathways to this, but how do you quickly get it to not have an exponent, to not be squared? Okay, so we know cosine 2u is 1 minus 2 sine squared u. I'm sorry, mu. right? And so this was one of the ones that we just talked about. And so if you, again, like if you didn't remember this expression of it, go ahead and think through. Use our old friend, the Pythagorean identity, right? And so maybe if you're just remembering that this is cosine squared minus sine squared, oh, but this is cosine can just be one minus sine, right? And there we've got that, right? So I'm going to go ahead and just rearrange this to solve for sine squared mu. Okay, so I get sine squared mu equals 1 minus cosine 2u over 2. Right, so that's you're quickly reducing the power. Like I see, let's say I know when I'm proving something or simplifying or solving, like I don't want it to be squared. This gets you out of that, right? This reduces the power. So these are equivalent. What about cosine 2u? Let's do something similar, right? So you know again that this is cosine squared minus sine squared, and let's go ahead and replace this time the sine squared minus with 1 minus cosine squared. And so this was one of the re-expressions as well. You get 2 cosine squared u minus 1. Just as we did up here, let's go ahead and rearrange that and solve for cosine. Right, so let's add 1 and divide by 2. So you've got 1 plus cosine 2u mu over 2. Right, so you've got 1 for sine, 1 for cosine, and guess what? 1 for tangent. So for tangent, we're just going to go ahead and set up the quotient here. The ratio that we know is sine over cosine. So that's going to be 1 minus cosine 2 mu over 2 divided by 1 plus cosine 2 mu over 2. Right, and when we go ahead and we solve for that, we get 1 minus, or we simplify that, 1 minus cosine 2 mu over 1 plus cosine 2 mu. Right, so these are what we call our power reducing identities. So we've got, in the last video we did sum and difference, and now we've done double and half, as well as power reducing. And again, like just think about how these connect and that they're not all happening separately. And this takes practice to like look for things and recognize things, and just make sure you're continuing to practice. So let's go ahead and use one. So use the half angle identity to find the exact value of sine of 5 pi over 12. So 5 pi over 12, we know is not a special angle, right? That's something we know. But we can express it in a different way so that we're going to look at it, so 1/2 times that, or something divided by 2 is going to give you 5 pi over 12. Well, 5 pi over 6, right? That's the same thing as 5 pi over 12. And 5 pi over 6 is a special angle, yay. Right, those are the best. So this is half angle for sine. And so if you recall, this is where it had the plus or minus. And let's come back to, is it positive or negative? I guess I could do it right now, but we'll come back to it at the end. I'll come back to it at the end. So you've got 1 minus cosine of the angle 5 pi over 6 over 2. Right, so the square root plus or minus 1 minus cosine of 5 pi over 6 is going to be negative root 3 over 2. We know that. That was the point, over 2. And then it's just a matter of simplification here. So this is 2 plus root 3 over 2 divided by 2, or times 1/2. So I've got plus or minus the square root of 2 plus root 3 over 4. We know what the square root of 4 is. So I've got the square root of 2 plus root 3 over 2. And is it positive or is it negative? Well, let's think about the unit circle. 5 pi over 12 is going to be in quadrant 1. And in quadrant 1, sine is positive. So I'm going to get the positive, I'm going to have a positive answer, a positive result. So it will be the square root of 2 plus root 3 over 2. Okay. Let's look at another one. So see how else this applies, right? So we did solving as well. So solving, you're finding where these intersect. So I've gotten, you're solving this over from 0 to 2 pi. So the sine of 2x equals the sine of x. So let's go ahead and first think, well, let's use double angle here, right? So this is the same thing as 2 sine x cosine x equals sine x. And now it looks like something more familiar. 2 sine x cosine x minus sine x, right? Don't just divide by it, we'd lose a solution or two solutions. And then I can factor out sine x, and I'd be left with 2 cosine x minus 1 equals 0. And then I can go ahead and use the zero product property. And sine of x is equal to 0 at 0 and pi. So there's two solutions. Those are fine. There's no issues here, right? And then where's cosine of x equal to 1/2 between 0 and 2 pi? At pi over 6 and at, no, it's not. Pi over 3, sorry guys. And then 5 pi over 3, right? And if we take a look at the actual graph of it here, you can see, and so this is 2 pi here, and so we're not including that. They intersect again, but we're not including that. So you can see, oh look, at 0 and at pi, and then at pi over 3, and at 5 pi over 3, right? You can see there's those points of intersection. Okay. Oh boy. Okay, so here we've got prove the cosine of 6x equals to, I'll erase a little. Cosine of 6x equals 2 cosine squared 3x minus 1. Okay, and our goal is to prove this. So I'm actually, this might seem different, but I'm going to go ahead and just work on the left-hand side. And I'm going to change that, or I'm going to rewrite that to be the cosine of 2 times 3x, right? I can see that I want it to be a 3x. So I'm going to work with that. And then I'm going to actually go ahead and I'm going to use the double angle identity here, right? And so you know that the cosine squared 3x minus sine squared 3x, right? It's like this is my theta. I might be able to get right to that at that point, but that's okay. And then I'm going to go ahead and I know the Pythagorean identity. So I've got cosine squared 3x minus, well, I know sine squared plus cosine squared equals 1. So sine squared is going to be 1 minus cosine. So 1 minus cosine squared of 3x. I'll distribute that minus, that's subtraction. It's cosine squared 3x minus negative cosine squared 3x. That's like a double negative, that's positive. 2 cosine squared 3x minus 1. Oh my goodness, that's the right-hand side. And we're done. Okay, so you can see how these tie in and apply. Oh yes, there's the work. So this just added some more to your knowledge and your identities. This was actually, I believe, the last identity that we're learning for these. So I would really encourage you to practice with these, and we will practice when we see you guys in class with the content that we've done in the last 2 videos, and just keep practicing and use the resources that are posted, and we will see you all soon. Thanks, everyone.